Okay, next up, we've got the 2006 differential equation FRQ. We are given a differential equation, dy dx is equal to 5x squared minus 6 over y minus 2 for y not equal to 2. Let y equals f of x be the particular solution to this differential equation with the initial condition f of negative 1 equals negative 4. Part A wants us to find dy dx, and so it's the first derivative and the second derivative at negative 1, negative 4. Well, the first derivative is given to us, so all we need to do is plug in negative 1 and negative 4. So we're evaluating the first derivative at negative 1, negative 4. That is going to give us 5 times negative 1 squared minus 6 over negative 4 minus 2. And that will give us 5 minus negative 1, which is equal to 6. And that may be the easiest point on this whole FRQ. Then we've got to find the second derivative. So before I plug in any points, I first need to find the second derivative. So for this process, I'm just finding the second derivative using a little bit of implicit differentiation. But first, I want to go back up to the way this is written, and I'm going to rewrite it to make that differentiation a little bit easier. So dy dx, 5x squared, but now I'm going to write this denominator in the numerator. So we're going to get minus 6 times y minus 2 to the negative first power. And that's just going to help us with using the power rule for that. So our second derivative with respect to x is going to be 10x plus, and I get a plus because I bring the negative 1 times the negative 6, times 6 times y minus 2 to the negative 2 power times dy dx. And that's the implicit differentiation piece, that dy dx. So that's our second derivative. Now, the last thing we're going to do is we're actually going to find the second derivative at our point negative 1, negative 4. So I'm going to plug the negative 1 in for x, the negative 4 in for y, but we know that dy dx is equal to 6 at the point negative 1, negative 4. So I can plug in 6 for that piece. So we've got 10 times negative 1 plus 6 times, when I plug a negative 4 in here, I'm going to get negative 6 to the negative 2 power times 6. It's a lot of 6s, a little scary. So what we are left with here is we're left with negative 10, and then just to simplify this middle piece here, I would get 6 times 6, and that would be like in the numerator, so that would be 36, and then this negative 2 puts this term in the denominator, so I'd actually get negative 36. Well, that's just going to be negative 10. Oh, negative 6 squared, excuse me, that's positive. So I get negative 10 plus 1. That gives me a negative 9. So each of these answers that we got here is worth a point. So 1 point for the 6, 1 for the second derivative, and then another point for the second derivative at the point negative 1, negative 4. Time to move on to part B. Question B says, is it possible for the x-axis to be tangent, so the x-axis to be tangent to the graph of f at some point? Explain why or why not. So if we have the x-axis that's tangent, if that's, the x-axis is a horizontal line. Okay, now if we have a horizontal line that's tangent, what that would mean is that it means that dy dx is equal to 0. So that's a horizontal line. If we want that horizontal tangent line to be the x-axis, then we have this other piece that we need to add in, and that means that y is equal to 0. So both of these things have to be true. The first derivative needs to be equal to 0, and y is equal to 0. So we're going to use both of these items in our derivative equation. So we know that dy dx is equal to 5x squared minus 6 over y minus 2. Okay, now I'm going to put in 0 for dy dx, and I'm going to put in 0 for y. And what that's going to do is it's going to give me 5x squared plus 3. And now at this point, we should be able to tell if this is even possible. Is this possible? And the answer is no. 5x squared plus 3 can never be 0 because this has got to always be positive. So what we would say here is that the x-axis will never be tangent to f of x. This is a 2-point question. Your first point really comes just by identifying these two pieces. That's a point, and then your actual work describing this and your conclusion being correct would be your second point. So we're up to 5 points total for the problem, parts A and B. Moving on to question C. Question C says find the second degree Taylor polynomial for f about x equals -1. So I need to find a second degree Taylor polynomial about f equals, about f, for f about x equals -1. So that means it's centered at x equals -1. So our terms for that would be f of -1 plus f prime of -1 times x plus 1, and then we get f double prime of -1 times x plus 1 squared all over 2 factorial. And now at first sight of this Taylor polynomial problem, we're thinking we're probably going to have to do a lot of work. But all this is given to us already. F of -1, we know that this is equal to -4. That was given at the start of the problem. F prime of 1, that's the same as our derivative dy dx evaluated at the point -1, -4, which we know is equal to 6. And then f double prime was our second derivative evaluated at -1, -4, which we found to be -9. So all we need to do is plug these 3 values into this and we have our second degree Taylor polynomial, which would be -4 plus 6 times x plus 1 plus, or minus, we could do it either way, -9/2 times x plus 1 squared. This is a 2-point question. What they gave points for here was they gave points for all the right coefficients. So we'll say 1 point for the coefficients, and then 1 point for having the x plus 1 and the x plus 1 squared. So that means you're centered at the right spot and you got up to that degree of 2, which the question was asking for. So 3 points for part A, 2 points for part B, 2 for part C. That leaves us with 2 points for part D. It's another Euler's method question. And for our Euler's method here, it says starting at x equals -1 with 2 steps of equal size to approximate f of 0. So again, we're going to make our 5 columns for Euler's method. You guys are getting really good at this now since every question has asked us about this. Delta y, again, equal to y prime times delta x. We start out with the point -1, -4. Our goal is to get f of 0, so we're looking for the y value when x is equal to 0. 2 steps of equal size, we're going from -1 to -0.5 to 0. That gives us a delta x of 0.5. This point in time, we are ready to start filling in our table. So, what's kind of nice is we already know what our derivative is at -1, -4, because we found that out. That's equal to 6. We use that piece in A and C. So now we take 6 multiplied by 0.5. It gives us a delta y of 3. I'm going to add 3 to -4, which gives me a -1. Now, this one might get a little tricky. We're going to plug in -0.5 and -1 into the derivative. When we do that, now you guys aren't going to like this, but you end up getting a y prime value of 13/4, those scary fractions. And then we're going to multiply 13/4 times 0.5. Same as multiplying by 1/2. That creates a denominator of 8. So we get a delta y of 13/8. When that gets added to -1, we get a value of 5/8. So f of 0.
John Sandler, please dial 4506. John Sandler, please dial 4506.
F of 0 is approximately equal to 5/8. And again, 2-point question, 1 point for your work, 1 point for your answer.